The concept of entanglement was introduced by Einstein, Podolsky, and Rosen in the context of a beautiful thought experiment, where they tried to show that quantum mechanics, as it's standardly formulated, is incomplete. That there's I'm sure you know that Einstein did not like this aspect of quantum mechanics, that outcomes are probabilistic, outcomes of measurements are probabilistic. I'm sure you've heard his quote that God does not play dice with the universe. So this thought experiment, which is called the EPR Paradox, was introduced to show that there's something wrong with quantum mechanics the way it's formulated, and that it's incomplete, that it's part of a larger truth, a more complete theory. For our purposes, in understanding entanglement better, it'll be useful to go through this reasoning of the EPR paradox. Okay, so let's start with where we were. So we already talked about the Bell state, which is this superposition of 0, 0, and 1, 1. And then we talked about measuring the Bell state, which seemed a bit paradoxical, because if we measure the first qubit, we see 0 and 1 with equal probability. But if we see a 0, then the new state of the system is 0, 0. And if we see a 1, the new state is 1, 1. Which means that now if the second particle is measured, no matter how far it is from the first particle, the outcome is exactly the same. The outcome of the measurement is exactly the same as the outcome of the first measurement. So this should be a little disturbing, because these particles can be arbitrarily far apart, and the measurements can be arbitrarily closely coordinated to be almost instantaneous, or to be space-like separated, so that even light did not have time to go from one to the other. So how could these two particles, how could these two qubits coordinate the outcomes of these measurements so perfectly, despite being so far separated? Well, as we said in the last video, you could imagine that the particles do this by coordinating their actions before they were separated, by actually flipping a coin and deciding that the outcome is going to be 0 or 1 based on whether the coin came up heads or tails, and using that same coin flip, both of them, so they are perfectly coordinated. But now let's look at a different property of this Bell state, which is what happens if, instead of measuring in the standard basis, in the bit basis, we measure in the sign basis. And this is where something very strange happens. So it turns out that the Bell state, which you can write as an equal superposition of 0, 0, and 1, 1, you can equally express it as an equal superposition of plus, plus, and minus, minus. So we'll see this in a moment. But before we do that, let's see what this implies, for measurements of these two particles. So now what this means is, if we were to measure in the sign basis, well, the first particle is in the plus state with probability half and minus state with probability half. But if it happens to be measured in the plus state, then the other qubit will be in the plus state with probability 1. And if it's measured in the minus state, then the other qubit will be in the minus state with probability 1. So now let's go back and see, how could these two particles coordinate their actions so perfectly, both in the bit and in the sign basis simultaneously, together? Well, one way they could do it is, of course, faster than light communication, because these two particles are so far apart, and we are measuring them at the same time, essentially, so that light did not have time to travel from one to the other in the interval between the measurement of the first particle and the measurement of the second particle. Okay, you can see why Einstein might object to that. What's the other possibility? Well, The other possibility is that when the two particles were together, they could have flipped two coins, one for the bit basis and one for the sign basis. And then they agreed that, let's say if the coin, maybe they agreed that for the bit basis they would answer 0, and for the sign basis they would answer minus. What's wrong with that? Well, what's wrong with that is the uncertainty principle. You see, the particles are not allowed to know if the bit value is perfectly determined, then the sign value is maximally uncertain. This is what we showed in the last lecture in the uncertainty principle. And so we are in a bind. Neither of these two possibilities seems reasonable. Relativity rules out the first, and the uncertainty principle rules out the second possibility. Let's look at it another way. One way we could carry out this experiment is we could measure the first qubit in the bit basis and the second qubit in the sign basis. And let's say we do these two measurements so close together that light didn't have time to travel from one to the other. So now, when we measure the second qubit in the sign basis, we know from this fact that if the sign value turned out to be minus, then the sign of the first qubit is also minus. On the other hand, when we measured the first qubit and it turned out to be in the bit basis a 0, well, we know that the first qubit must be, now both in the bit basis it's in the state 0, but also in the sign basis it's in the state minus. Surely this contradicts the uncertainty principle. So these were the difficulties that EPR tried to highlight with their Gedanken experiment, or the thought experiment, which has now been named the EPR Paradox. And what they believed was that, in fact, the way out of all this was that the two particles carry with them all the information necessary to locally decide the outcome of any future measurements. In other words, possibly, they believed that this uncertainty principle was actually incorrect. And Einstein spent the rest of his life really looking for a hidden variable theory, a local hidden variable theory for quantum mechanics. Now, what does standard quantum mechanics say about all this? Well, what quantum mechanics says is that as soon as the first qubit is measured, let's say in the bit basis, the entanglement between the two qubits is destroyed. So because the new state is now either 0, 0 or 1, 1. In each of these two states, you can say exactly what the state of the first qubit is and the state of the second qubit is. So if the state is 0, 0, the state of the first qubit is 0 and the second qubit is 0. So these are completely unentangled states. Now if you measure the second qubit in the sign basis, it no longer reveals any information about the first qubit. So if you were to accept quantum mechanics, the rules of quantum mechanics, there's no problem with all this. It's just that the rules of quantum mechanics seem so strange. This notion of entanglement seems so strange. The other thing you can say about the rules of quantum mechanics is, well, the other thing you could complain about is that it appears as though the two particles are they're communicating information between them. Even if these two particles are in the entangled state, how could they instantaneously come up with the same answer randomly? How could they randomly choose 0 versus 1 and plus versus minus? So the answer to this is that, in fact, what the two particles are achieving is some sort of correlation between the two sides. But you cannot use this correlated outcomes to actually transmit any information from the one particle to the other. In other words, suppose that you were sitting at the site of the first particle and you had a bit of information. Let's say the bit happened to be 1. And you wanted to communicate it to somebody in a different country. And you happen to hold one half of this Bell state, and your friend in this other country held the other half of the Bell state. What you could try to do is communicate this bit that you have to your friend in this other country via this measurement of the Bell state. And so if you measure your qubit in the bit basis, and if it turns out to be 1, then your friend, his qubit, if he measures it, would also say 1. But of course, this happens only with probability half. With probability half, when you do a measurement, you get outcome 0, which is what you did not want. And then your friend will hold a 0. So he gets a bit which is 50-50, 0 or 1. And he gets no information at all about the bit that you're trying to transmit to him. And so what you can show is that, in fact, through the means of entanglement, it's impossible to transmit any information from one party to another. All you can do is you can achieve this kind of coordination where you flip the same random bit. And this doesn't violate the theory of relativity or speed of light considerations. Now, Einstein believed to the end of his life, which was about 20 years after he published this EPR paradox, that there was a local hidden variable theory, that quantum mechanics was incomplete, and he spent 20 years searching for this local hidden variable theory. As it turned out, in the 1960s, John Bell, the physicist whom we name Bell states after, discovered that there's an actual experiment you can perform which would demonstrate either that quantum mechanics is incorrect or that there's no hidden variable theories consistent with the way nature behaves. Soon afterwards, these experiments were carried out, and they are consistent with quantum mechanics and inconsistent with hidden variable theories. So in the next lecture, I'll describe to you what this experiment is and the principles behind it. It's actually quite remarkable that already in the second week of a class with no background in quantum mechanics, you can describe in full detail this experiment, which would have saved Einstein 20 years of his life thinking about an alternative to quantum mechanics.